Welcoming everyone to the first session of the day. In this session, the esteemed panelists are going to discuss about accelerated exploration for unleashing unrealized hydrocarbon potential in mature and frontier basins. To commence the session, I would like to introduce the chair for the session, Dr. C. Lakshma Reddy. Dr. C. Lakshma Reddy is an upstream oil and gas professional with more than 3 decades of diverse experience covering the entire gamut of E&P industry. He has worked in field operational areas like Ankleshwar in western India, in Assam Arakan Fold Belt in northeast India, and in offshore and onshore areas of Krishna Godavari Basin in Andhra Pradesh. We welcome you, sir. I would also like to introduce the session co-chair, Mr. K.S. Shaktawat. Mr. K.S. Shaktawat has more than 38 years of technical and managerial experience in the upstream hydrocarbon exploration and development activities. He served in different technical and managerial capacities in ONGC and Directorate General of Hydrocarbons. Sir has worked on various assignments, including geological and geophysical interpretation, hydrocarbon prospect mapping, resource estimation, review of exploratory and development well locations, and many more. He was superannuated as Executive Director from ONGC Delhi in 2018. Sir, may I now request you to kindly commence the session, please?
First of all, thank you very much. And I welcome Dr. Bjorn Wygrala first. And Dr. Wygrala is a geological advisor for basin and petroleum system analysis in Exploration, Cologne, Germany. Dr. Wygrala has 40 years of experience in geoscience, especially in petroleum exploration. He will be presenting on play-based exploration. So welcome, Dr. Wygrala.
Right, good morning. Thank you for the introduction. And could you just confirm that you can hear me and that you can see the cursor on the screen?
Yeah.
It's working? Okay. Okay, the title of my presentation is The Play Concept as a Keystone in Exploration Risk and Resource Assessments. And keystone is a very interesting term from architecture. It's a special feature that supports a structure. And we'll look at two examples of the applications that are very closely related. We'll look at exploration risk assessments and petroleum resource assessments for undiscovered resources. So quick first with a few definitions. And I assume that everybody, or most people will know what a play is, but there might be students or people just starting in the geosciences, so I'll start with a few definitions. First, a play, a geographically delineated area where several geological factors are present so that producible petroleum could be proven. And the controlling geologic factors are the petroleum systems elements. They include reservoir, cap, and source rock. The term geological features is very important here, especially, for example, for resource assessments where we talk about a feature-based approach. And the features that we have are the lead, something we can identify in the subsurface that might have the potential to entrap hydrocarbons. Prospector is a feature for which more data exists, which can be mapped. The discovery is a feature with confirmed producible petroleum. Field is a feature with proven petroleum reserves. And here you can see this cartoon on the right-hand side from the Norwegian Petroleum Directorate, standard cartoon. We can see the basin outlined in green, plays outlined in pink, and we have geological features in here. Play risks, a very important term, very useful term, is that play has been proven or opened by making a discovery. And so you can see the discoveries here, dark brown, and we show we have an unproven play up here, no discoveries yet, and a proven play down here. And this is a fundamental step. We all know in exploration, if we can open a new play with a discovery, that is a huge success. The discovery proves the play concept and obviously affects the play risks. So if I'm looking at prospects and a discovery has been made in the same play, then my chance of success is much higher. Discoveries do not need to be commercial, but they prove that all of the elements and processes of the petroleum system coexist in at least one location in the play. So just a couple of basic definitions. Play-based exploration is a term that is used quite frequently. Major proponents such as Shell have presented and applied the concept widely. And you can see in here a pyramid which shows the exploration workflow in a way, from basins to plays to leads to prospects to drill-ready prospects. And you can see in this pyramid here, this is based on publication by Milkov, a huge number of tasks that need to be done. We won't look at all of these in detail. All we need to see here is the ones that have been colored in green. These are tasks that are directly related to first petroleum systems and then to play analysis. So we'll just go through with the simple subdivision of these workflows. We'll first look at play to prospect risking, exploration management. The first part is the geoscience foundation. We'll obviously start with looking at the data. We need to organize the data so that we have efficient access. We then have a huge task, the G&G work, geophysics and geology. We need to set standards, and then we go through a process which results in interpretations, and these need to be fit for purpose. So we need to have the right dimension, scale, and scope of these interpretations. The next step is then petroleum systems. This is also a huge task. It starts with a basin analysis. So we look at regional geological history, global analog studies, critical too, because we often do not have much data. We then do basin petroleum systems modeling, and the conclusion, the result of this work, is that we have better understanding of the risk elements in exploration. So we define a standard risk model, and this covers, for example, reservoir, charge, trap, and seal. So the petroleum systems understanding is the foundation for the next part of the work. The next part is then a play risk analysis, and this in a way is the keystone because it's a building block between the geoscience foundation and the next part of the assessment, which is prospect risking and portfolio management. And you'll see down here, this arrow down here, this is a probabilistic approach. We transit here when we go through the play risk analysis to probabilistic assessments because we have many uncertainties in all of the data. We need to understand the effects of the uncertainties on the results. So we have prospect risks, which are determined by both the regional play risk and the local prospect risks. And then we go through into portfolio management, where we manage the results. We look at management strategies, and we can, for example, get prospect ranking based on management strategies and the geologic risks. So let's look at an example. This is a very recent publication. I think it's a fantastic story of exploration in the last few years in the Eastern Mediterranean. So you can see here the Mediterranean Sea. We're in the Eastern Mediterranean, and this has been a very successful area, especially for biogenic gas exploration with some massive occurrences. So we look at the exploration history, and you can see the bottom axis here is in years. We're looking at about 50 years of exploration, and we can see something very typical in this basin. Just note too, we're also looking, everything is plotted in recoverable resources, not in place. The industry standard is recoverable. And then we can see phases where we have gradual increase in reserves and resources, and then big steps, sudden steps. So we have, and this is when a new play is opened. So the play terminology is very interesting. You can see these steps, new plays are open, we have big jumps in the resources, and the new plays are opened by companies taking an approach which is often described as high risk, high reward. So in this case, the Zor discovery, massive discovery here, very unusual configuration, a new type of play, and this was opened by E&I. You can see other companies, Noble Energy, BG, BP, who have opened new plays in the area. In between, we have phases where we have gradual increases, and these are managed with a low risk, low reward approach, which needs to be done. The important point here, high risk, high reward, and this improves our ability to open new plays. Another example, at first sight, as you're obviously in India, and I've spent a lot of time in India, you might think for a moment, if we're looking at this area over here on the west coast, this has maybe some similarities to Kerala Konkan. We look at this basin here, we have an exploration history, also 50 years of exploration in this area, 1,300 kilometers coastline length, that's this part here of the coast, 24 wells drilled, 0 commercial discoveries in 50 years of exploration. The area we're looking at, it's obviously not India, we're not looking at the west coast. In this case, we're looking at offshore West Africa. We have a lot of E&P success in neighboring countries, Angola to the north, and some good activities in South Africa as well. But here in Namibia offshore, we only have one non-commercial gas discovery, which was made in the 70s and still is not commercial. This is the Kudu field. So this is 50 years, no success. This year, in the first quarter of this year, so we're only looking at the last few months, 2 very important play opening discoveries were made, one by Shell in deep water, approximately 2,000 meters, you can see it over here, and another one by Total, the Venus well in ultra deep water, 3,000 meters approximately water depth. So in a very short time, these 2 companies have done a fantastic job of cracking the key. 50 years of search, no discoveries, and both of these have seem to have very good commercial potential. So one we can see again here, these are the play openers. Use the high risk and high reward in this case approach. So the first part was exploration. How does the play risk analysis fit into exploration? It's a keystone. Second part, we'll look at assessments of undiscovered resources. So we've looked at the first part. This is what we can see here, going up to exploration risk assessment. And for resource assessment, the geoscience foundation is identical. It's exactly the same to what we do in exploration. But we go from the play risk analysis. We use a different subdivision of the areas. Instead of going to prospects, we go to so-called assessment units. So the plays are subdivided into assessment units based on geology, risks, and strategic requirements. And once again, we have a standard risk model, which is based on our petroleum systems knowledge that we use to assess the risks in each assessment unit. This then enables us to build the YTF database. We have data features. You'll see the features, very important. Discovery histories, lead, prospects, etc., calibration data. And then we can aggregate the resources from the different assessment units and map them. We create what we can often call, a nice term, a digital atlas. So a few definitions here, very important terms for resource assessments. In place versus recoverable. In place is the potential hydrocarbons that are actually in the reservoirs, but these do not indicate the commercial value because we know that we can only produce a small share of the hydrocarbons. So the standard term that is used for resource assessments in the industry is the recoverable. This is the oil and gas that can be produced. This is the commercial value that we're interested in. The next important definition is the so-called success case. versus the risk case. If we are successful, we want to know what could we discover in an area or in an exploration well if we are successful. But we know that if we're looking at portfolio of assessment units or wells, not every well, not every assessment unit will be a fully successful case. And so we need to risk it. We need to take the geologic risks into account. And so the result here is that industry standard best practices in exploration and in resource assessments, that the results are reported as risked recoverable resources. So key requirements for a resource assessment, the methodology is play-based, it's probabilistic because we have many uncertainties that need to be taken into account. It is geology-based. We saw the G&G foundation in the workflow, and it depends on our understanding of the plays and the petroleum systems in the basins. Several key references that do a very good job, and especially that publish results. Bureau of Ocean Energy Management in the US, Norwegian Petroleum Directorate, and we'll look at two simple classic examples from each of these authorities. So this is, in a way, you could call it a digital atlas. So in this case, BOEM in the US have assessed the offshore areas, and you can see Alaska, Atlantic, Gulf of Mexico, Pacific, and these are the total results. You can see the mean, and you can see undiscovered, technically recoverable. Technically recoverable. So everything's only plotted as recoverable. An example from Norway. We're looking here at the country here, this coastline, roughly 2,000 kilometers. And we go from south, where we have a long exploration history, up to the frontier areas in the north, the Barents Sea. We have here approximately 70 plays that are being defined in here in these different areas. And you can see about half the plays have been proven. We have discoveries in about half the plays in the National Play Catalogue. Results here, if you look at the totals, this is risk mean, undiscovered, recoverable resources. This is US offshore, huge potential. This is Norway. It looks small, but this is just because the US is so big. So we have to remember in Norway, very active exploration, probably on average 40 to 50 companies, including most of the major international oil companies, active in E&P in Norway. So they have done a fantastic job of attracting investors into the country. So a quick look at India, and most of you will probably be aware of a project, especially at ONGC, that was done, a play-based probabilistic assessment of all 26 basins in India in 2017. The project was assigned by DGH to ONGC, all of the work undertaken by asset team members at the regional offices. This is optimum decision because everything we've seen already depends on the knowledge and understanding of the G&G data that is developed. And obviously the asset teams at ONGC know this. They have this experience. So this was a good decision to have it done by the ONGC asset teams. So here you can see the 26 basins. First remark here is that the ONGC asset teams developed a series of project reports for each basin, and these reports follow a standard format. So there are approximately, I've just guesstimated this, 10,000 pages of reports. This is a fantastic project, fantastic result to have a standard for all of the petroleum systems and basins in India. So this is the first part of the 26 basins. Remember, in Norway, we had a national play catalogue of roughly 70 plays, very well explored area. Here in India, the basins were subdivided in this project into approximately 180 plays. And then the plays were subdivided into smaller units, which have different risks, different geology, and we end up with a total of 800 assessment units in the country. So this is a huge amount of work. Every assessment unit was risked using a standard risk model, and we have in the database, the first version, roughly 50,000 input data entries for this project. If we just look at some of the results, a very important remark here, these results are not yet published. So what I'm showing here is schematic. I can't show any numbers. The data and the results are owned by DGH. But what you can see here, this is a schematic presentation. The basins are all ranked. So we know, if you have access to the database, exactly which are the best basins in the country and what are their resources. Then we can go into each of these basins and select a play. So once again, this is just schematic. This is not a specific play. And we can see exactly which play has the best potential. Then, because it's all in the database, we can select a play and we can look at the assessment units. So we can also rank, and we can see exactly in each play which are the best assessment units, which have the best potential. So this is from a presentation I was invited to present in an SPG meeting in India, in Jaipur in 2017, after the project was completed. But once again, I can't show the data, I can't show the results because they have not been released. They're owned by DGH. But you could, for example, go back to the previous slide. What are the undiscovered resources in India, for example, compared to Norway? Well, that information is available internally. So the value for the government of this work is we have a standard reference for G&G knowledge. So remember, these probably 10,000 pages of reports, a fantastic resource, really amazing work done by the teams. We have a database with an industry standard play-based probabilistic assessment. Every basin, play and assessment unit in the country. These are based on integrated petroleum systems analysis and play evaluation. So you can see once again the play concept is critical. And the current status, this is also public knowledge, is that the database is being updated with new information obtained since 2017, when the project was, the first part of the project here was completed.
You please sum up, we are approaching time.
Okay, yes, so this is summary and conclusions. So 3 key points here. The first is the topic, play-based exploration. And what we can see here is that play risk analysis is the keystone. The general workflows that we're using here for exploration risking and YTF resource assessments are identical. They're built on the play-based exploration concept. The workflows only differ when we reach the final stage here. The probabilistic assessment in exploration is prospect. In a resource assessment, it's an assessment unit. And in exploration, we develop portfolio management capabilities. And in a resource assessment, we have a YTF database. We then looked at 2 very nice, very recent examples. These are this publication was only released late last year. We saw Namibia drilling results from this year and 2 major successes. Conclusion here, typically new plays are opened with a high risk, high reward strategy. And we've seen in the examples, this is more likely to be followed, the strategy, by internationally operating oil companies. The low risk, low reward strategies are then applied, they have to be applied as well, to realize the full potential of a play. This is play analysis and exploration. And here we look at summary play analysis and resource assessments. Resource assessments obviously an essential tool. We need to know what we have, domestic supplies versus what do we need to import if we do not have sufficient domestic supplies. And they are essential to attract investors with the ability to open and prove new plays. So we saw a very nice example from Namibia where Shell and Total have actually not just proven the new plays, but they've opened the country for production. So play-based and probabilistic industry standard best practices must be applied to assess and to present the results. I'd like to thank the organisers of the meeting, Ministry of Petroleum and Natural Gas, DGH, and I can also be contacted. I'll just leave my email address on here anytime. And thanks once again to the organisers for letting me present this talk. Thank you.
Thank you very much. Okay, so welcome Mr. Adhikari. He's a geologist with 15 years of experience and in new ventures, exploration and appraisal and development. He will be sharing his experience on mature and frontier basins, petroleum systems and play types in Kembe Baramura Rift area. So I welcome Mr. Adhikari. Please go ahead.
Thank you so much. So I'll start. Oil and gas plays a vital role in the economic development of any nation. And India is the third largest consumer of oil and gas after USA and China. And petroleum products are a major component of our import bill. And it is said that for every $10 rise in the oil price, India's growth can decline by 30 to 40 point basis. So despite the potential in the Indian sedimentary basins, the oil and gas production has been steadily declining for the last decade. And I believe there is no alternative for India but to increase the domestic production. And the billion-dollar question is, how can we do that? Now, this presentation is focused on Rift Basin with a specific focus on Kembe and Baramura basins. What I would also like to talk about is what new approach can we use to find new plays with specific examples from these two basins. And we will also discuss a couple of areas where we think the government can help us in opening up more plays. So before I begin, I would like to thank the Upstream AHAD and also the Exploration and Subsurface team for both Rajasthan and Kembe for helping me put together this presentation. So the overall outline of the presentation will be, I will have one slide on the global rift basins and the potential of rift basins. And then followed by the potential of Baramura and Kembe basin, and we will compare the Baramura and Kembe basin with the global rift basins. We will also look at, as I was discussing, the new approach to find new play types, petroleum systems and play types in Baramura basin and Kembe basin. And also we will see how we can link the Baramura to Kembe, and then we will end with some concluding remarks. So just to begin with, the rift basins are the third most prolific basins in the world. And there are multiple hydrocarbon-bearing basins around the world, 9 of which are highlighted in the map on the right side of this slide. And based on the sediment water supply rate and the potential accommodation rate, we can divide the rift basins into 3 types: the underfilled, the balanced filled, and the overfilled. What we know from the studies is that balanced filled rift basins has the best source rock potential, and both Baramura and Kembe happen to be a balanced filled basin. And that shows how immense potential that we can have in these 2 basins. Now, both Baramura and Kembe basin have similar geological history, and as you will see in this presentation, Baramura basin can be considered as the northern extension of Kembe basin. And the rifts formed by 2 main phases of rifting. First, during the Jurassic, the Africa separated away from India, creating this northeast-southwest tending rifts. Followed by that, towards the end of Cretaceous, Seychelles separated from India, creating the northwest-southeast tending rift, which is the tertiary rift and the main petroleum system in this region. Now, in this slide below, in the gray panel at the bottom of the slide, I have summarized some of the exploration timelines, significant timelines for these 2 basins. The initial exploration here happened based on sparse 2D and gravity and magnetic data. Lunes 1 was the first discovery in Kembe way back in 1959. It was only in 1999 when we got the first discovery in Baramura. It was the Gouda 1 discovery. Now, Baramura basin here is a very classic example of a frontier that has been converted to a prolific basin. by doing detailed studies. So earlier we saw some of the potential studies and exploration risk assessment in the previous presentations. So we ourselves had did some detailed integrated petroleum systems modeling in Baramura. And with the help of that, we could break the paradigm and then take the brave pill, as I say. Even in the 90s, the basin was not recognized. The Gouda discovery was not enough to suggest that there was a prolific basin hidden under these rocks. And there was doubt on the source rock and the reservoir, especially in northern Baramura Basin. But then in 2002, Cairn became the sole operator in Baramura. 2002, exactly a couple of decades ago, was a very good year for Cairn. We had tasted success in that very same year in Cambay offshore with Lakshmi, Gauri, Parvati, and Ambe. Building on that confidence of the successes, Cairn challenged the existing paradigms in North Baramura. We did a detailed 3D basin modeling, and then we finally took the brave pill and ended up drilling Mangla, Bhagyam, and Aishwarya in 2005. The rest is history. So both Cambay and Baramura are prolific basins of India. However, if you compare them to the creaming curves of other rift basins around the globe that we saw in the map previously, there is still a long way to go. When we say that a basin is mature or a basin has creamed out, we say that based on old ideas. And every time a new idea kicks in, the creaming curve gets a new life. And we see that over and over again in various basins. You can see that in Gulf of Suez here marked in red. Even after 50 years, the actual kick up in the creaming curve happened after 50 years of exploration. So the question now we need to ask ourselves is, what is that new idea that can ramp up the creaming curve of Cambay and Baramura? This slide might have an answer. So this could be one possible way of finding the answer to that question. So the plot on the left shows the age-wise distribution of discovered in place in Cambay in red and Baramura in green. Cambay has a discovered reserve of 3.8 billion and Baramura of 1.7. And based on our studies, the yet to find of conventional oil and gas in Cambay is 1.5 billion, and in Baramura it's 3 billion. And add to that the unconventional potential. So there is so much left to discover. So where are the new plays? Now to understand that, we can where we can get the new plays from, we need to bring in innovative technologies, and we need to understand the basin with help of petroleum systems modeling. And these two terms I'll be keep repeating in the presentation: new technologies and integrated petroleum systems modeling. And we need to start by asking the right questions. Now the table on the right is one tool that I personally use that helps me do just that. And I will explain that in detail in the next slide. And this is a specific example from North Cambay. Here the play is defined by a. So I believe most of us geoscientists do this exercise intuitively. However, I personally find this table a very useful tool to ensure that we do not miss any play types. So in the different columns, we need to put together the possible traps that we can think of that exist in our area, in our basin or sub-basin. In the rows, you have the stratigraphy. Thus, in a single table, you can put together all the possible play types in that area. Further, you can divide each cell into concept, lead, prospect, and discovered field. So the proven plays are highlighted here in gray. So these are the plays that we have already existing discoveries in that region. So that's proven. But then once the table is ready, the team needs to brainstorm the possibility of each new play type where we do not have a discovery. Then ask themselves, how can it work? Not why it cannot work, but we have to approach this from positive mindset and ask ourselves, how can it work? In which possible geological scenario can we make this play work? And while answering the question, one has to be unbiased and unconstrained in their thought and leave behind the preconceived notion. It's an integrated approach, as you can see, to de-risk the leads and prospects. And you can see the amount of data that has gone into this. The more data we can integrate in this, the better. And this is where we believe that the government can help us. Synergies and knowledge share between all the operators working in a particular basin, coordinated by DGH, will help us in creating better models. And thus, it will help the country in finding more hydrocarbons and more new play types. Now, in the next couple of slides, I would like to talk about some of the new play types we have found in Baramura. Now, the first one is Durga, and that is a brilliant example of how, with the help of this structured approach, we have opened up a new play in a mature basin. So the basin margin Dharvidunga play was always risky, and multiple geoscientists have put their heads around this. And now here we are with this discovery in Durga. We have opened up a new play type. And there are plenty more other new play types around that we can open up by following the same approach. So there is the Fatehgarh Lake margin, the older Mesozoics, and the Neoproterozoics. We don't know the Neoproterozoic potential in Barmer yet. And also, obviously, there is the unconventionals that we are working on. So going back to that creaming curve of Barmer Basin, when we compare to the other areas, all these new play types show that we still have a long way to go. So now I will move a bit south and try to link the Barmer Basin to the Cambay Basin. And as I was saying, Barmer is kind of a northern extension of a Cambay Basin in more than one ways. And this is what I found really interesting. This has come up based on the sparse 2D, but more importantly, on the right side of the screen, you can see the new FTG data that we acquired. So this is how we are leveraging new technologies to open up new plays. And in this section, you will see that Barmer Basin on the left, the seismic section and the play model that's shown on the left side of the slide. In the left, you have the Barmer Basin of that section, and on the right, you have the northern Cambay Basin. And what's intriguing is that they look exactly similar. Now, we have used FTG to guide our interpretation to validate the seismic because it's poor quality 2D seismic that we have here. We are working on the new data that we have acquired. But this is very, very interesting because we know that Barmer Basin is highly prolific and northern Cambay Basin is not explored that much, but they look exactly the same. So based on the integrated GDE, we now know that this region has the right provenance for good reservoirs in the time equivalence of Fatehgarh, and which is very, very different from the old pads we know of in further south in Cambay. We know the petroleum systems work in the north, and there shouldn't be any reason why it shouldn't work in just further south in its extension. So with a simple idea, an entirely new realm of possibilities have opened up. Can we repeat 2005? But before we take the brave pill, we have to do this. And this is the petroleum systems that we did for Cambay. It's a similar approach we used as in Rajasthan. Unfortunately, we don't have as much data in Cambay as we have for Barmer. The more data we can put into this, the better this model will get. So in the next two slides, I will talk about a few of the new play types that we have identified by following the same approach we discussed earlier. As discussed in the left side of the screen, this is not Barmer Basin, this is northern Cambay. And you can see that exactly same Mangla Bhagyam Aishwarya-like foot closures are there. We are de-risking this play type based on our FTG data, niche technologies like fluid inclusion studies integrated with the seismic. And also on the right side, you can see with help of old reprocessed data, the reprocessed legacy data and advanced seismic interpretation, we have opened up. This is not really an entirely new play type, but we have opened up this new concepts, this new leads and prospects, and we have made a discovery in Jaya within the Hazard Sands in South Cambay, and we can see that there are more potential around. Apart from that, there are other potentials as well in Cambay that has not been explored much. One is obviously the Deccan fractured basalt that works in Barmer. We have a couple of areas like Padra and Karjan where it works in Cambay as well. So there must be more around. And what is very, very interesting is the Mesozoic. We have not really explored the Mesozoics of Cambay. There are few wells that have been drilled through the Deccan basalts into the Cretaceous, and we know that there are Cretaceous sediments below the Deccan. Now, for the first time ever, based on our new FTG, we can see clear evidence of a northeast-southwest trending Jurassic rift in North Cambay. So this again could open up an entirely new play type in Cambay based on such innovative technologies. And obviously, the study of unconventionals in the Cambay shales is itself in a very nascent stage here, but we don't know what kind of potential is there in the unconventionals of Cambay. So just to conclude, the creaming curves of Barmer and Cambay might look completely different a decade from now. The exploration maturity, as I said earlier, is defined by old ideas. Now, to change this creaming curve, we need to challenge the preconceived notions and break the paradigm. Use all available data to make the integrated petroleum systems model Maybe we can find a way to transfer knowledge between companies with help of DGH, use new technologies and workflows to find new play types. And after de-risking, there comes a point when we need to take the brave pill. And we believe that government can provide encouragement to companies to use new technologies like we did with FTG and FIS. And finding a mechanism to swap the additional work program with the MEP would go a long way in encouraging companies to leverage new technologies, take more risks, and kickstart the dying creaming curves that we have. So I will leave you with that thought. Thank you.
Okay. Thank you very much, Mr. Adhikari. So we can go to next. You please. Hello. Hello. We welcome Dr. J.K. Samal, and he is currently General Manager Geology at ONGC Limited. He has more than 10 years of experience in exploration development of Assam and Assam-Arakan basins. Dr. Samal will talk in depth about exploration in Assam and Assam-Arakan fold belt. So, please start your presentation.
Thank you, sir. Good morning to all of you. This is the image where we'll be talking of that exploration, the opportunities and challenges. That is the full thrust-based exploration in Assam-Arakan fold belt. Next, please. Yeah. So the presentation sequence which I'll be covering, what is the importance of this fold thrust belt in hydrocarbon exploration and how they host hydrocarbon. Then coming to fold thrust belt in Assam-Arakan, what are the geological consideration and how our exploration journey has started, what are the lessons we have learned and what are the way forward. Then technology, how it is the key driver, how it has enabled us to improve in our understanding, to add more reserves in our kitty bag. Then what are the opportunities and way forward. Next, please. Let's first have a look on the global perspective, how fold thrust belt they do host the hydrocarbon reserves worldwide. Next, please. This is the key slides. We all need to understand that these are the areas which are typically perceived as difficult place to explore for several reasons, where many companies they do not venture into because of difficulty in terrain, because of difficulty in cost of exploration, in many other reasons. But on the other hand, these are the areas which do host huge potential of hydrocarbon reserves. So challenge and opportunities, they are hand in hand. When we look at the statistics, you can see the 14% of the world's discovered reserves, they are in the fold thrust belt. And in the right side, when we look at the diagram, we can see the yellow pie diagram, that is the fold belt potential. And when you look, still 15% of the global total undiscovered resources that do lie in the fold thrust belt. So what does it tell? It tells it has got a lot of promise for large accumulation and underexplored status, which justifies for further exploration. So at this juncture, if we put a barrier in effective exploration in fold thrust belt, that means we are keeping the untapped resources intact, that as unexplored. So the focus should be, as per the theme of this conference, that accelerating exploration program. These are the areas, fold thrust belt areas, they do have huge scope for further enhancing our reserve and for finding out more hydrocarbon from different new plays and consolidating our existing plays. Next, please. Next slide. So coming to the Assam and Assam-Arakan fold belt, what are the exploration opportunities and challenges? Next, please. This is the digital elevation model of Assam-Arakan Fold Belt. The first, when you look at the digital elevation model, you can see the topography, that is the elevation part, and that gives you the inherent complexity, that gives you the inherent challenge. But in the right side, you look the statistics, the undiscovered and discovered resources, and the conversion of resource to reserve. When you look at the statistics, we do have the potential of 1633 MMT resource, out of which only 178 to the tune of only around 11% we have converted. I think the screen sharing. Yeah. So when you look at the statistics, with only 11% of conversion, it speaks a lot. There is a huge potential, untapped potential. We need to go further. Next, please. In fold thrust belt, the primary control is geological control, structure, and tectonics. So when you look at the Assam-Arakan Fold Belt, we can see it has been generated because of the oblique subduction below the Eurasian and Burmese plate, and it has got a implication. What implication? Through time, if you look at the stress pattern, from the start of the image, there are 3 stresses. In the right side, you can see phase 1, phase 2, and phase 3. Phase 1 is related to your westward compression, and phase 2 is related to opening of the Andaman Sea, and phase 3 is upliftment of the Shillong Massif and Doki Fault. So these 3 stresses that has impacted the structure generation, and it is in turn controlling the hydrocarbon accumulation pattern in the Assam and Assam-Arakan Fold Belt. When you look at the Indo-Burmese wedge, our Tripura Kachar area, they fall in the outer wedge. So that gives you good positive scope for the accumulation pattern, because in the inner edge, there is more deformation and there is more breaching or less accumulation. Next, please. So when you look at the Assam-Arakan Fold Belt, which comprises Tripura, Kachar, Mizoram, Manipur, have a look on the shape of the fold belts, shape of the folds. You can see the S-shaped. It has got 2 implications. One, I explained that the stress pattern. The other is the concomitant sedimentation pattern that is in the Sylhet Low. So that is acting as a buttress towards west of this fold thrust belt. So when you move towards west, your deformation intensity that decreases, and you can see from the bottom of the diagram where the distance between the 2 anticlines that decreases towards east. What does it mean? It means that there is a intensity is more, there is a more elevation, so erosion is more. So we have to look for different play types, even if it is a more formed state in Mizoram area or towards eastern part, more eastern part. There we have to look for the subthrust or other play type. But towards west, you do have the less deformation, so you will have all the ideal situation for the accumulation part. So overall, we do have the opportunities in all setups. We need to target with a specific play approach of different play types. Next, please. how we have started exploration. In Tripura area, you can see 22 structures that has been identified, and out of which already we have probed in 18 structures. And similarly, in the Kachar, you can see there are 29 structures. In these areas, there are the exposed structures and subtle structures or concealed structures. We have got good discoveries of Agartala Dome, Banaskhandi. All these are the concealed structures that has given us good volume of reserves in the fold belt, which has got similarity to Tita structure in Bangladesh also. So what I mean to emphasize over here that in the fold thrust belt, the surface geology and the geology, the structure pattern that plays an important role. So again, we'll be discussing these structures, how in the other areas. Now we can see these are the structures where the numbering we have done, but whatever the in between areas, that answer will be getting towards end of my presentation. Next, please. So where
I request Dr. to expedite please a bit.
Sir, yeah.
We are lost initial time, so please expedite a bit.
Yes, please. We have started the exploration from structurally simple anticlines. This is the example from Baramura, where we discovered from 1975. But 75 versus 2022, what are the addition and what is the understanding improvement that let us see. That time we didn't have much seismic. We had limited data. We had a limitation in deciphering the subsurface structural geometry. But through time, what we have learned. Next, please. Next slide. Yeah. So the same Baramura structures, you can see initially the deciphering the subsurface geometry, it was difficult. But now we do have the seismic data and we have the better understanding on the faces also. Initially, we have only a geological field map from which it is difficult to capture the three-dimensional heterogeneity. But now with the help of seismic and towards right, you can see the structural balance section where the axial asymmetry of the structure that can be deciphered from the section. And towards the bottom of the image, you can see the facies map that has captured from seismic. It has captured the heterogeneity. So what is the lesson we have learned? That is the change in perception through time. Initially, because of the inaccessibility or unavailability of the data which were perceived as a risk, now which was high risk element, now it can be perceived as a low risk and which can give us the high reward. Next, please. Next. So when you go to the description of any area for the hydrocarbon accumulation part, we need to have analogy. Next, please. This is the area, Tripura Kachar area. This is surrounded by huge gas field of Bangladesh, which have got similar tectonics and structure. So that is giving us a lead to go for further exploration, intensify our exploration in Assam-Arakan Fold Belt, because it is having 32 TCF in Bangladesh. Next, please. I'll give you a good example. Next slide. This is the recent discovery in Bangladesh, that is the Jakiganj, Bangladesh, which is just towards north of our Patharia structure from India and Bangladesh border. Jakiganj, where it has been discovered from the depth of around 2870 meter, and it is giving a very good rate, the gas rate. The same Patharia structure where we have drilled 5 wells and 2 wells are gas bearing. But the catch is over here that the gas which has been discovered, you can see in the seismic section, that is from 1200 meter depth. And the deep meter data tells that the deep is around 4 to 5 degree. So if you go to the plunge and the 28-meter depth that is in the Jakiganj, the equivalent towards the south of Patharia structure, there you can expect the good accumulation of gas. However, how it was not perceived, because if you look at the seismic image, that is the imaging issue, which is an inherent challenge in the fault thrust area. So 2 leads, Jakiganj discovery, that is giving for further exploration that the deeper plays that we can attempt for. And the next is, this is the well that has been drilled successfully with in addition of 47% hydrostatic pressure, that is in the overpressure zone. So that also gives you confidence that successfully completing a well in high pressure zone and targeting a deeper page. So these are the leads which gives us impetus in our exploration program. Next, please. What are the play types over here? In adjacent area, that is Bangladesh, that is the structural and stratigraphic. So initial stage, that is structural, and slowly we are coming through, we are transgressing through structural to combined and stratigraphic, purely stratigraphic also. Next, please. So now coming to the fold belt of Assam-Arakan fold belt, what is the play perception and what are the primary control on its accumulation? Next, please. So when we look at from the West Tripura to East Tripura, as I told that depending on the intensity of deformation, you will be finding different kind of structural types existing over here. And when you look at the play type, major play type over here, that is the Bhuvan play that acts as the reservoir and Rangi play that acts as the reservoir. The Rangi that we have only explored in the Kachar part, that is the towards eastern part. So this figure, what it indicates, when you look at the 1, 2, 3, 4, in the western part, we have the plays that is well established, that is the upper and middle Bhuvans. In the eastern part, we have the plays that is the lower and lower Bhuvan and Rangi of Oligocene age. So what it encourages us? It encourages us that the successes in deeper plays subsequently, that is encouraging that to probe more for the deeper plays towards western part. So the bottom line is there is no dearth of source, reservoir and seal rocks, but the difficulty is locating the traps amidst this complex structure and tectonic setup. Next, please. Now the paradigm shift, which you can see, if you look at the global diagram, there is a paradigm shift from structural to stratigraphic. And when you look at the success rate of after 2000 and up to 2020, there is a giant leap in all the entrapment styles, out of which the most eye-catching is the stratigraphic and combo entrapment. So that initial stage fault thrust belt, which were envisaged as the only structural type, that also encourages us to put forth the application in the Assam-Arakan fault belt, and which we have already been doing, and we are getting successes also. Next, please. So when let's start that how we understood properly for the structural styles over here. Still there are a lot of things to be understood. When you look at the deformation in fault thrust belt worldwide, there are both thin and thick skinned, and we have seen that the thin skinned, they account for more than 60% of the reserve in fault thrust belt. And in Assam-Arakan fault belt, next please. Now in Assam-Arakan fault belt, you can see the structure is mainly of thin skinned, that is primarily it starts from the detachment fold and subsequently with compression it is fault bend and fault propagation fold. And the seismic section you can see from Agartala Dome to Khubal area, how the structurization or change in structural pattern it is changing. Now the challenge is, what is the challenge over here? Here is in the bottom part there is a field photograph that is from the Spiti area of central Himalaya, where you can see the asymmetric anticline that is mimicking the Baramura, Atharamura, all these structures. There we do have the seismic imaging issues, And the key issue is the understanding the subsurface structural geometry or deciphering the axial asymmetry. Here, the structural modeling or restoration technique, that technology will help us to overcome these issues to bring out a valid geological section and to get a success out of it. Next, please.
You to expedite, please.
Please. Next, please. So when we have the analogy with the Eastern Cordillera, Colombia and Zagros Mountain, you can see the similar structural trend, structural grain and map pattern that speaks of Assam-Arakan Fold Belt with the other basins of the world which have got good producing hydrocarbon. Next, please. Now we can see the from the image, you can see the structural map pattern and grains. Next, please. Now, here comes the, I talked about the new plates. Now we can see the success in the Colombia, Eastern Cordillera, where you have the duplex structure and subthrust success. And the similar things which we are yet to prove in Tripura Kachar. One example is from the seismic example is from the Baramura and the field example. So here you can see the subthrust and duplex structure, which are it will give a distinct class of play, separate play that will open new areas for future exploration also. Next, please. Similarly, next is the cross faults. The cross faults, they also play an important role in this fold thrust belt, and we have the analogy with the Colombian central foothills. You can see here the cross faults. You need not to have. You can see the image in the image. You can see the pool limit. The hydrocarbon pools, they are separate, and the accumulation pattern speaks that there is some barrier in between. So in these areas, the cross faults, they play an important role in identifying the separate traps and independent hydrocarbon pools. Next, please. But what is the challenge over here? Because I am addressing the challenge and opportunity. The challenge is in the left side, you can see from China Basin, there is a cross fault, but they are not visible in seismic scale. So you have to go for the transfer sections or serial cross sections. There, in the right side, I'm showing that how integration is the key to de-risk the things and to bring out the proper structural pattern. Here you can see in the Kachar example how Landsat images and drainage pattern, all these trends, they help us to identify the cross faults and bring out the structural different structural patterns. Next, please. Now, timing of the deformation. What it implicates? The implication is the preservation potential of a fold thrust belt. They are being enhanced when they are relatively young. So in our case, when we have carried out the structural modeling part, the restoration, it speaks that the onset of deformation, they are post-TIPM, that is less than 2 millennium. And now you can see the analogy with the worldwide also, that Colombian Caribbean Basin, the younger the age, the better the preservation potential, and the better scope for future YTF potential. Next, please. Now the major thing is the paradigm shift, that is the stratigraphic trap exploration, which initial stage it has not been attempted in the fold thrust belt. Next, please. In the Bangladesh part, we can see the stratigraphic trap that has given them a good success, that is relict, cut and relict features. And towards east, I can show you the stratigraphic entrapment, which the cut and relict features in the Sundulbari field and in the channel features in Khubal field, and the attribute map you can see from the 3D seismic, which has helped us in deciphering the reservoir geometry, that is in the Kunjaban fields and in all the other fields. They are giving good success, and they here the lead is we are in the start phase, or we have just started the exploration last 10 years we have started the attempting the stratigraphic entrapment, and this is going to change the scenario of exploration in fold thrust belt in Indian scenario. The stratigraphic entrapment that will give us the success. But now the challenge is that how to delineate these facies part. So we are the place perception here at this juncture, we are changing through time from structural to stratigraphic. Next, please.
Please expedite, your time is over.
Yes, yeah. Next, please. So this is the inherent problem, that is the tidally influenced area. You will have the limited extent reservoir bodies. How to exploit? Next. So now this is our end of the session presentation slides. How the technology will give us, and right time, right application of technology will help us in play opening, play consolidation, and play development. Next, please. We have a lot of technologies we have applied and we have got success. That is the passive seismic tomography that we have applied in Kachar area. The full tensile gravity gradiometry you can see towards right. In addition to the structure, there are other prospective area that has been identified for expert location. The major thing is the acquisition parameter, the swath geometry and wide azimuth survey, where you can see towards bottom part the seismic section where the anticlinal part is well imaged. Next, please. Next slide. The spatial processing that also gives us, you can see in the left side there, if we are going for the stratigraphic trap, then our image it should be properly enhanced. So with the application of the spatial processing technique, you can see, and towards right you can see the robust velocity analysis methodology that has given us the clarity in the gathered data. You can see how the flattening and random noise they have been removed, and that has helped us in advanced seismic studies. Next, please. So in seismic also, conventional seismic, we have always challenges in discrimination of the patients. For that, we need to go for the high resolution, that is the inversion studies, pre-stack inversion studies. This is the good example where you can see how it has given us good opening of the opening and consolidation of the plates in the Tripura fold area, fold belt area, where the inversion studies, they have helped us in identifying the exploratory and development prospects. So these are the techniques that is helping us to overcome the challenge out of the conventional seismic. Next, please. Another thing is artificial intelligence. That also the application of AI and ML, you can see in the same Tripura area, West Tripura area, where you can we can get the most probable phases. That is we are able to predict the reservoir properties that using the artificial intelligence technology. In the middle Bhuvan and upper Bhuvan, you can see how the phases we are bringing out. Next, please. Similarly, the structural modeling that gives you preparing the valid geological model for the risk reduction and guide in seismic interpretation. Next, please. So, what are the opportunities and what the exploration strategy we should adopt? The three, I'll put it in three forms. That is the new finds.
Samal, please sum up. We have extended your time. Right?
Yeah. New finds vis-a-vis exploration maturity, consolidation of new finds, and the opening of new areas. Next, please. So the recent success in deeper plays, that is enhancing us, that is giving us more opportunities for the deeper plays, that is lower Bhuvan and Renji. Next. Here, as I told that the subthrust and duplex structure, which already we have the Russian field example where they have discovered out of after 1913, again 1960 in the subthrust case they have discovered. Next, please. And the more important is the flank, plunge, and synclinal height. As in my first slide, I had told what is the in-between areas. Those areas are very important and key in finding the future targets. And now my last slide is, next please. Now my last slide is When we want to reserve accretion, we do or volume expectation more, then we'll have 4 ideas. That is, if it is a matured play, then we'll apply their frontier ideas and frontier technology. If it is a frontier play, then let us apply mature ideas and mature technology. And we can see the risk-reward matrix where the maturity, exploration maturity, which is very high, that is in the top part, and in the bottom part where we do have the relict features, we do have the subthrust plays, we do have the HP plays, high pressure plays, and logistically inaccessible plays, where we can impart the technologies and we can bring it to the, we can get the good reward. So overall, these areas, they do have a huge scope for adding more and more hydrocarbon to accelerate the exploration and to enhance our production in overall Indian hydrocarbon scenario. With this, I'd like to thank the organizing body for giving me the opportunity, and I'd like to thank ONGC for giving me opportunity to present the work in the current forum. Thank you. Next slide, please. Thank you.
Thank you. Thank you very much, Dr. Samal. Thank you.
Okay.
So now we welcome Dr. Shoup. Welcome Dr. Robert Shoup. He is a board certified petroleum geologist with over 40 years of experience in basin analysis, regional studies, new play generation, and project management. He is the chief geologist and a course instructor for Subsurface Consulting and Associates. He will be presenting on petroleum system modeling. Welcome, Mr. Shoup.
Thank you. All right, so if we can go to the outline, we're going to cover, look at basin analysis first. So looking at the Earth model, and then from that, we'll build our tectonic framework, and then the stratigraphic framework. And then once we have that defined, we can go in and look at the petroleum system evaluation, looking at source rocks, migration, reservoir, trap, and seal. So we can go to the next slide. So for petroleum system modeling, we have to make sure that our interpretations properly define the Earth model. And our interpretations have to tell one story with no disconnects. And oftentimes we see multiple interpretations coming together for a single Earth model, and there's parts of the story that don't match other parts of the story. And the other thing you have to do is make sure that your interpretations are valid in the first place. So next slide. So what we have to do is, Sorry. So we want to make sure that we've defined the basic elements to define the Earth model. And notice that in the Earth model, there's actually nothing about petroleum. So we need to have multiple consistent Earth models, which are a powerful tool for defining the plays and then helping us reduce the risk. So going to the next slide, we can see that one of the first things we have to define is the shape of the basin and the overall structure of the basin. Then next, we go to look at lithology. After lithology, we'll look at porosity and permeability distributions, so reservoir quality. Then we're going to look at pressure and temperature and other reservoir engineering data. And then finally, we'll look at the fluids, but that would be all the fluids, not just the hydrocarbons. So the next slide, then with all those up, before we build the Earth model, we have to evaluate the data. And we're a data-intense industry, so we have a lot of data to look at. So it's important that we use all of the data. In fact, from our work, one of the principal causes of dry holes is people not using all of the data. So looking at rock data, going to the next slide, we have outcrop data that should be incorporated in our study. We have geologic maps, we have mud logs, we have the cuttings from the wells, and we have sidewall core or whole core data. Going now to well data, we have to look at all the well logs. We also have to look at the well reports, including the paleo reports, the mud log report, and any petrophysical summaries that have been provided. Then coming on to the seismic data. In most basins, we'll have some 2D. We may have some 3D surveys as well. And then we want to look at the various attributes like AVO and similarity and some of the other attributes, as well as seismic amplitudes. And we have to also analyze the velocity to see if we have velocity gradients. Then we'll have remote sensing data. So we'll have radar or LIDAR, we'll have gravity and magnetics, or subsurface resistivity in the EMGS. Then next, we have to look at all of them and look at or make a number of maps. And that includes evaluating satellite images if we're working onshore, or SEEP images if we're looking offshore. We have to look at the topographic maps, the geologic maps, gravity and structure maps, as well as cross sections. Then going on to reservoir engineering, we'll need to evaluate pressure, the temperature, and if there's any fields in the basin we're looking at, we'll have to look at decline curve analysis. And then we'll look at the hydrocarbons and the fluid data. So we'll need to look at and evaluate the RFTs or DSTs. We have to look at vitrinite reflection, and then non-hydrocarbon gases. We'll want to look at the mud logs for shows and any geochem data that we have on hydrocarbons that have been produced. So once we've looked at all the data, or at least have all the data in our hands, what we want to do is define or understand whether we have all of the elements of the petroleum system present. And we're going to start by looking at the tectonic framework. And in doing that, we want to see how the basin was formed. We want to be able to define the size, the shape, and depth of the basin, and what lies beneath the basin. What is the lithology of our underlying strata or basement? Then we have to look at the stratigraphic framework. So what types of sediments filled the basin, and what was the provenance for those sediments? So looking now at the tectonic framework, the first thing we want to look at is the basin geometry, the size, shape, and depth. And that's a function of the basin type. And that's going to be determined whether the basin was extensional, compressional, or strike slip. We also have to look at the basement lithology and the basement history. Usually we start by looking at magnetic data. So that's a measurement of the density or magnetization that we have. So here's the magnetic data for India. And that gives us an idea of where the basins are and some of the underlying magnetic systems. We also want to look at the gravity data. So gravity is a measurement of the Earth's gravity, and it's free of any topographic or isostatic effects. And usually we look at Bouguer gravity. And what that is measures the mass of Earth between the gravity meter and the datum. And so we can see in the figure here that when we have a rooted mountain system or continental system, Bouguer gravity goes down below our reference. And then when we go out to oceanic crust, it comes above the reference. And here's the gravity map for India. Next thing we want to do, looking at the tectonic framework, is define the basin type. So we have convergent margins or divergent margins. And we will have, in some of the margins, we'll have either a transverse margin or a passive margin. So looking at some of the tectonic frameworks for the various basin types we have, for rift basins, depending on the strain conditions that are present, we'll see one of three geometries. We'll either see asymmetric rift basins, or we'll see symmetric rift basins, which are formed by mantle upwelling and collapse into the due to tension, or we'll have a mixture of horst and grabens in our rift basins. If we continue rifting and go and open it up to we'll get a passive margin developed on top of our rift basin. And in our passive margins, we'll either see salt tectonics if we have a salt layer deposited, or we'll see shale-based tectonics. In our compressional settings, we can have trenches, which form as we subduct a slab below a continental mass. Or we can go to four-arc basins, which will have a slope basin in front of the trench, and then we'll have a basin behind the subduction zone. And then that's usually before we get to the volcanic arc. Or we can have a back arc basin. So that'll be behind the highlands and associated with the volcanics. We can have a foreland basin. So before our thrust sheets, we can have a basin in front of those. And then going to our strike slip systems, we can have pull apart basins. And then the other thing we have to look at, and this is a slide from the Natuna basins, we have to look at the basin histories. And in the case of the Natuna, we had a rift basin subsidence, then we had reactivation and inversion, which uplifted some of the shallower sediments. So one of the things we see if we go to the next slide is that exploration has historically been conducted from the top down. So we drill the shallow traps or basements at the early stages of exploration, generally because they're shallow, they're easier to map and identify, and they're cheaper to drill. Unfortunately, when we do this, next slide shows that many of these wells do not actually get into the petroleum system. So if we look at the next slide here, it's a seismic profile out of the Malay Basin. We need to conduct exploration from the bottom up. And since the distribution of source rocks and reservoir facies are controlled by the geometry of the basin, a critical first step in defining the petroleum system is to map the base and the top of the source rock section. Next slide. So in mapping the base of the system, we have to actually pick basement. And it turns out for most basins, picking the basement, or at least the base of the petroleum system, is actually a fairly large challenge. It typically is an iterative process, and the interpreter has to look at multiple displays, including various attribute displays, different color bars, as well as the conventional seismic display. So here's just the basement pick on those three lines. And you can see that they don't always look like what you would be picking as basement. And I can also tell you from experience that what you pick on dip lines or in lines will not necessarily automatically match what you pick on the cross lines. So you do have to go back and forth. You also want to change the scale. So we typically work at a vertically exaggerated seismic section, often 6:1. But you also want to redisplay it on occasion with 1x or 2x, because that gives you a very different perspective of what the structure looks like. Now, one of the things about mapping basement on our next slide here is that basement often extends below seismic or beyond the limits of our 3D data, which means that mapping basement often requires mapping or hand contouring. And a lot of our interpreters get kind of nervous when they have to hand contour. Once we've defined the tectonic framework, we have to look at the stratigraphic framework. So we need to define the basin fill by looking at the provenance, which will tell us what kinds of sediments are coming into the basin, the burial history, and then that in turn will help control the heat flow. And we have to look at whether our reservoirs are going to be clastics or carbonates or an unconventional type reservoir. We're going to start by looking at the provenance. And we have to understand the tectonic history of the provenance, the underlying lithology of the provenance, and the weather of our source area, because that's going to control the rate of sediment input, and it also controls the type of sediment that enters the basin. After we've looked at that, we're going to now look at the burial history. So we have to look not just at the burial, but if there's been any uplift or exhumation in the basin. These factors are going to control reservoir quality, and they're also going to strongly influence migration pathways and migration history. Next thing we have to look at for the stratigraphic framework is the heat flow. So we need to understand or map or plot out the geothermal gradient. And we have to also take into factor any tectonic events that affect the heat flow, such as rifting or volcanic activity, because these things influence the reservoir quality and will also be a fundamental control on expulsion timing. Looking at the stratigraphic framework, then, once we've looked at the data, we can construct a chronostratigraphic cross-section or Wheeler diagram. The one you're looking at here is from the Nankan-Sam Basin. So you can see that in the Oligocene, we had rifting, and then continuing into the upper Oligocene, we went into the post-rift, mostly clastics. Then as we go into the early Miocene, we have clastics still, but now tidal bars in a tidal estuary. Then we start to see carbonates, and then at the very more recent, we see the progradation of the Nankan-Sam in the basin. So chronostratigraphic cross-sections here give you a good understanding of the basin history, and you can post with them the gravity and magnetic striping, the sea level curves, and any of the paleo data that you have to further help you understand your stratigraphy. You also want to make geologic cross-sections. So this one's out of the Great South and Canterbury Basins of New Zealand. And when you make a geologic cross-section, you want to show the geology, not just pick your correlation tops. So you want to put your reservoirs in there as well as your all your other sequences. Now, another thing you can make, we're going to get to the next slide, is the size form section. So you start by interpreting your seismic with your key tops. Then you apply a seismic stratigraphy interpretation plus your understanding of the depositional models to get to the next slide, which shows then a seismic-based cross-section. So it is in two-way time, but now we're showing the lithology. So now that we've conducted our first pass at understanding the tectonic framework and the stratigraphic framework, we're going to go to the next system in our step in the outline here, which is to look at the petroleum system. And to do that, we'll look at source, migration, reservoir, trap, and seal. So again, going back to our Earth model, all of the elements of the Earth model are linked, and we have to have a consistent interpretation. So seal, reservoir, and source rock, those are controlled by the depositional systems that are working in the basin. Those are in turn influenced by the provenance and the uplift and subsidence rates that are going on in the basin. Those in turn are related to the basin type. And then going forward, we'll see that the basin type is controlled by the structural systems, and those in turn control the migration, trap, and seal. So that's how our petroleum system elements are related. So the first three, seal, reservoir, and source rock, we define those when we define the stratigraphic framework. For our understanding of migration, trap, and seal, we define those by understanding the tectonic framework. So again, and you've heard this in the other talks, our petroleum system has 5 elements to it. We have the source rock, which is organic rich rock that is capable of generating hydrocarbons. We have to understand the migration pathway, which is the connection between the source rock and the reservoir rock. We then have the reservoir, which is a rock with porosity and or permeability, such that the hydrocarbons can flow out of the rock to the wellbore. We have the trap, which is a structure or reservoir pinch out, configured in such a way that it can store hydrocarbons. And we have a seal, which is a non-permeable rock that can prevent hydrocarbons from exiting the trap. So we're going to look at source rocks first. Next slide. So source rocks are the foundational element of the petroleum system. So if we don't have a source rock, we don't have a play. So going to the next slide, understanding the source rock is the key to understanding a basin's petroleum potential. And again, if we have no source rocks, we have no petroleum system. So we need to look at 2 things. We have to understand how organic rich sediments were deposited, and then we have So going to the next slide, to have source rocks deposited, we have to have high organic productivity. That usually requires light, so we're depositing source rocks in the photic zone. We have temperature controls, we need a source of nutrients, and we need to have low turbidity or low input of clastic sediments into the basin. Then going for organic preservation, we have to have one of two conditions, or preferably both. We have to have anoxic waters so that the organic rich material does not decay. And then also it helps to put it rapidly bury the source rocks. So going to the next slide here, we see two figures on the left. We see marine source rocks and lacustrine source rocks. And we can see that on the shelf edge where we have fairly high sediment input rates, we're going to have low TOC percents. As we go out into the slope and basin, we're going to have moderate to high TOC content. And then on the matrix, we can see that where we have high sediment input rates and low or high or oxic events, we get non-source rock deposition. If we go to low sedimentation rates and oxic conditions, we typically see gas-prone source rocks deposited. When I go to the preservation on the vertical axis where I have anoxic conditions with high sediment input rates, we're going to get lean or oil-prone source rocks. And when I go to low sedimentation rates and anoxic conditions, we're going to get rich oil-prone source rocks. Now we can and should map source rock elements such as total organic carbon. Now to contour TOC or any other source rock indicator like VRE, we need to understand what is controlling the source rock distribution within the basin as well as the richness. Another thing we can do looking at the seismic profile here, we can look at the distribution of source rocks by looking at the seismic sequence here. So in this case, we have a rift basin. The top of the Sindh Rift section is shown in magenta. The base of the Sindh Rift system or basement is shown in red. And what we're going to look for here is organic rich shales. And these typically exhibit strong amplitude anomalies. And a method you can do if you go to the next slide is you can threshold the color bar to enhance the appearance of anomalies. So the example here shown is the RAI2 color bar in Kingdom. Normally when you pull that color bar up, you get a default range of 0.2 to 6.2, or 6.2 to minus 6.2, sorry. But you can threshold that, so reset that color bar range from minus 20 to 20, so you're looking only at the extremes. And what that typically does then is you see that your organic rich intervals or your DHIs will illuminate and the rest of the seismic tends to go pretty blank. So you can use that along with the basin geometry to start mapping out the distribution of your source rocks. Most of you are aware that there's three types of source rocks. We have algal source rocks that are typically found in lacustrine settings, although they can also be deposited in subca environments. Type 2 source rocks are lipid, are resulting from planktonic deposits, and our type 3 are humic source rocks from coals. So here's just a slide showing what algal source rocks look like. So you can see we get nice bedded layers of organic rich material, either in lacustrine settings or in subca settings. Planktonic source rocks are deposited typically in warm climatic conditions and in areas favorable to upwelling currents. And then humic source rocks are essentially deposited in swamps or marshy areas where we get good deposits of peat that turn into coal. Now, once we have buried the source rock and begin to heat it, it will start to generate hydrocarbons. And generally at around 30 degrees C, organic matter begins to change into kerogen. And at 60 degrees C, the kerogen begins to expel us into oil. And then at 150 degrees, the source rocks begin to generate gas. And then at about 225 degrees C, the source rocks become over mature. Now, one of the things you can do to understand the migration pathway is, again, come back and look at some of your attributes. So the seismic line shown here at the top is the similarity attributes, and we can see that some of the source-prone intervals seem to show leakage up some of the faults into the shallower section from the source rock section. Another thing to understand the migration pathway is to map faults. So the faults play a significant role not just in migration of hydrocarbons, but also in trapping hydrocarbons and formation of structures. So we'll look at the last two in a little bit. But when we're looking at migration of hydrocarbons, so we can take a look. This is a seismic profile offshore Mozambique, or onshore Mozambique. And what we see is that the migration pathway is going to be out of the basin, generally along either carrier beds or the fault plains. And if we look at the next slide, what we're going to look for here is areas where traps can capture regional migration of hydrocarbons. So we need to see dip away from the regional dip that can capture migration into a structure. Otherwise, migration will just continue out of the basin. And for most plays or basins, there's going to be multiple migration pathways using both carrier beds as well as faults. And as I already mentioned, you can use similarity attributes to try to map those migration fairways. So we have on the left the map of the similarity attributes showing a bunch of red and yellows. Those are the faults that are migrating hydrocarbons out of the source rock interval and into the reservoir formations. Another thing you can do is make cross sections and then post on the cross sections the oil and gas windows from your geothermal gradients. So this is a cross section out of Vietnam showing the present day position of the oil and gas windows. The next slide shows a map of the basins, and it overlaid on top of that are the areas that are where we see the that are in the oil window and in the gas window, and then a large part of the basin here is over mature. And then using the structure and the isochord maps, we can also put the migration vectors onto the map. And to do that, you're going to again look at any of the information you have for source rock maturity, and then make your cross sections. Then you want to map the fetch by looking at, again, at the flow vectors as they come out of the oil and gas windows. Now here's the same two cross sections, but we've palinspastically reconstructed them back to 23 million years ago. We're showing again the presence of the oil and gas windows. We see some of our source rocks are now beginning to enter into the oil and gas window. Some are still above the oil window. And we go to the map, we can then again post the maturity, showing the gas window, the oil window, and at 23 million years, we had no area that was over mature. And then again, we post the fetch to see how the hydrocarbons will migrate out of the basin. And we can use that then to start qualifying some of our play concepts. Then we have to look at the reservoir. Typically, we look at sandstones or limestones, or we can look at things like fractured basement or volcanic dikes and other things that can have fractures that may hold hydrocarbons. Looking first at clastic reservoirs, there's either delivery systems, which are going to be our rivers, and those will be braided or meandering or anastomosing or incised. And if we know the depositional environment, we can actually come in and understand the model enough to start mapping reservoir distribution with a fair amount of accuracy, even with little or no well data. Once the sediments get to the basin, we're going to get dispersal systems. We'll have aeolian that are widespread wind deposits, or we'll have deltas or alluvial fans or submarine fans. All three of those are low-bait systems.
Dr. Shoup, please expedite. We are running out of time.
Okay. All right, so carbonates, basically carbonates grow in place. They're developed in tropical environments, and the fundamental control on the distribution of carbonates is water depth. And the environments that we have are tidal outlets, carbonate ramps, carbonate platforms, and slope margins. And to understand where the distribution of those reservoir systems are, you're going to want to make gross depositional environment maps or paleogeographic reconstructions. Next thing we have to do is define the traps. And again, we're going to look at the role that these play in trapping hydrocarbons. So fault traps are closures against faults. We can have up-thrown or down-thrown closures. And I'll caution you that we drill a lot of dry holes on maps that have the faults improperly mapped. So you do want to make fault surface maps and look at the behavior of the contours of the fault and integrate those with the horizon to make sure the faults are properly positioned. Then we're going to have formation of structures. So we'll have growth fault rollovers, detachment folds, or fault bend or fault propagation folds. I'll just quickly show examples. Here's a growth fault example. Or we'll have salt withdrawal mini basins where we have salt deposit in the passive margins. Here's a detachment buckle off a shore of Nigeria. If you have a fault bend fold, here's the structural model and a map of a fault bend fold or a fault propagation fold. And all of these folds have a relationship to the fold geometry or the fault geometry, so they're pretty predictable. And then an example of some of the anechelon folds associated with strike slip faults. Last is seal. We have to look at top and lateral seal. To evaluate top seal, you're going to look at the fracture gradient. To look at lateral seal, you want to look at cross fault juxtaposition. You can do shale smear factors, or you can do shale gouge ratios. And the shale gouge ratio is essentially the inverse of the net to gross sand ratio. So another way you can evaluate seal is to make a sand percent map and overlay that onto your structure map to define seal risk. So those are all the elements of our Earth model. And again, we want to look at all of these elements to help us define then the petroleum system, looking at source, migration, reservoir, trap, and seal. So that's it.
Okay, thank you very much.
Here what to do?
Okay, now
Can
I speak now?
Yes, sir.
Okay, we welcome now Mr. Borgohain. He is the General Manager Exploration Basins and HOD Oil India Limited, Tulyajan. Mr. Borgohain has earlier served as General Manager of the Gabon Exploration Project in Africa. He will be presenting on new plays in Assam Shelf. So please go ahead. He is on mute, I think. Borgohain is mute.
Hello.
Yeah.
Huh?
Okay, we welcome Mr. Borgohain, and I repeat it. He is General Manager Exploration and HOD in Oil India Limited, Tulyajan. Mr. Borgohain has earlier served in General Manager in Gabon Exploration Project in Africa. He will be presenting on new plays in Assam Shelf. Please go ahead.
Sir, a little bit of technical hits actually, sir. Can you hear me now, sir?
Yes, you are audible.
Yeah. So, good afternoon, everybody. Myself, Trailukya Borgohain, General Manager from Exploration Basin. Already you have introduced me. Now I will be talking about Assam Shelf, basically, which is lying in which is the triangle zone between the Himalayas in the north and Nagapatkai in the south. Now let us talk before entering into the details of the basin. I would like to talk about the plays. The definition of the plays already Dr. Bjorn has described it. But for us, I would like to reiterate the definition again. It is a family of undrilled prospects and discovered pools of petroleum that are believed to share a common gross reservoir, regional topsill, and petroleum charge system. Plays are essentially reservoir defined, and therefore a single rock may charge number of reservoir defined plays. A single reservoir defined plays may be charged from different source rock. This particular definition is working very well in case of Upper Assam. If you look at the plays and the source rocks actually. So we have almost about 7 plays working in our basin, almost 7 plays, and we have only 3 source rock mainly. You can say that in especially in oil suppression areas we have the Lakadong Langpar cells and carbonaceous cells, and beryl argillaceous coal cell sequence, and the lower beryl coals. These are the main source rocks, and these are feeding all the reservoirs. And if you talk about Lakadong and Langpar, we can say that these are in-source plays, and for beryl also you can say that is the in-source play. But for Tipam and Girujan, we can say that these are the plays which are lying above the above source plays. If you think about the source to play connectivity kind of relationship. So apart from these plays, do we have any more plays? We'll talk about that in the later slides. So as of now, we have the understanding like this, that we have some proven plays, like already we have told that Lakadong Langpar, Beryl, Tipam, Girujan. These are the major plays, and there are 2 more plays like already proven but poorly exploited. There is the Kopili play and Norpu play. Also, Selo, Tipam, and Girujan Namjang plays in mature areas are also observed in some of the areas. We have recently drilled one structure in Lakwagaon in recent years, and this is not only a structure basically, but this is a structural prospect. So we'll discuss about that. And stratigraphic Tipam play is already working in this basin, but these are all these are under exploitation. And the future plays, we have identified some of the plays that we'll show in the later slides. Yes, these are some of the structural styles, mostly in the Paleocene Eocene. You can see that the plays are mostly located in the prospects are located mostly in the extensional fault blocks, or but however in the beryl section you can see that sometimes they are in the inversion structures like Naharkatia, maybe Kusijan, those areas. We have both extensional structures in both beryl and also in Tipam, but mostly we have the extensional structures and inversion structures in the Tipams and beryl. So we all know that the maturity of whatever maturity we are getting from the wells in these areas, in the main producing areas mainly. So whatever maturity we are getting is in the source rock is not that mature. So the main postulate here is that the pod of active source rocks are lying in below the thrust belt in the southern side mostly. And if we can find any source rock in the northern side, maybe some Gondwanas from the Himalayas are there in the northern side, and anything is happening on the northern side, then that can aid to our new plays. So the extension of plays are constrained by mainly the cap rock and reservoir rock coupling. Basically, the Lakadong Langpa reservoirs are facilitated by the Prang Narpu Kopili cap rocks, and these are extended quite towards the northern side, even all throughout the basin in Upper Assam in our areas. Although there are thickness variation towards the northern side, that the thickness of the Paleocene is decreasing. On the other hand, the Beryl Girujan play beryl, tipam, and beryl, argillaceous cells, Girujan cells, and clay facies also diminishes towards the north. Means that is what we call decom Cataloni areas. You may know that this is the central basement high areas. On north of those areas, you don't have too much of beryl, argillaceous, Girujan cell, and clay facies. So it diminishes towards the north. So and it limits the extension of plays in to a great extent. Then comes the thrusting and faulting. Definitely, thrusting and faulting is helping us in having the plays. Also, it is helping in leakage and destruction of the hydrocarbon at the end. One interesting factor in our basin is that we are finding commercial plays down to commercial hydrocarbon to a depth of over 5,500 meters in Mechak area. So you can think that whatever stratigraphic section lies above those areas, we should always think about exploring those areas. So this is what I was talking about. Is that this is the play probability map of Lakadong Langpar, basically a Paleocene Lower Eocene section. So you can see that the whatever probabilities we have, the highest probability is in the central basement high areas. And we have drilled some of the wells in the north bank and eastern flank also. And we see that the play probability decreases towards north and towards the east. But one interesting factor is that these central basement high areas is turning towards is running parallel to the Brahmaputra along the Siang River or Brahmaputra River towards the north. So you can see that this particular area where we have given the play probability as 0.5 to 0.7 in this particular green area. So this is one of the most promising areas for us for future exploration. On the other hand, this has got logic behind it. Is that whatever we are getting thickness in the north bank of the river Brahmaputra is that from the west to east, you can see that the section number 2. Section number 2 from west to east, the whole Paleogene section is increasing towards the east. That means the petroleum system, whatever we are thinking towards the eastern side, might exist also in the northeastern side of the basin. So the zone we are talking about in this particular red circle, red semicircle, red ellipse is the zone we are talking about. Next comes the beryl and tipam system. These are limited. Like already we have told that beryl argillaceous and also Girujan is missing in the northern side. So because of that, this the probability of plays in these areas diminishes. But we have not demarcated it as a 100% no play area. We have only done some play probability analysis. That these are some of the areas where you can get some in the northern side also. You may have some beryl and tipam plays. It is not that it is completely dry. We do not want to say that. This is the Girujan play map. So like already I have told that from south to north, the probability is decreasing because the thickness you can see in the north-south section. You can see that towards the north, the whole the Girujan thickness decreases towards the northern side. Recently, we have if you look at this particular map, these red areas are the high areas. And the one in the colors with deep colors in blue are the low areas. And if you look this map in the first place, then you will say that we should go for drilling in this particular areas in the north. But our analysis said that we are not going for beryl play in northern side, and we tried to find a structure in the south. We have a very good reservoir in the beryl oil field in the eastern side is the Moran, And also along that particular alignment of the fault, you can see that the one very big structure in Thaura is also there. But the prospectivity of Thaura is not as good as this particular Lakwagaon area. So you can see that the plays play very different kind of role in in understanding the reservoirs. So now this is another one that the first well in here is in the well is in the Jangoni area. This first well was a dry well. The first well was a dry well, but we proposed a new well in the in Tipams in the based on the attributes and also on the structural point of view. Then we got a good gas play in the gas in this particular play. So these are already proven and these are under exploration. But next comes the proven but unexploited plays, Kopili and Narpu. I know that Kopili is being already exploited in the ONGC areas, especially in Lakwa and those areas. But we have discovered Kopili in our areas, but we have not done much of exploitation in these areas. So we have, especially in Baramura area, we have seen that this 4716 meter Kopili sand gave inflow of oil, which is a good one, means is a light oil, 36.5 degree API. Then comes the Narpu play. Narpu play just lies above the Lakadang area, Lakadang reservoirs. So you can see that only in the eastern side the Narpu is developed. So we have done some studies on this, and we are trying to develop these Narpu areas also. So what plays the major role in our plays? So fault reactivation is apparently sealing structures may play a very vital role. Means it may be a very interesting that the fault reactivation may or may not may help in not having the hydrocarbon in already sealed structures. Then phasis change comes, then migration and charge. Then comes seal. So this is one example from our central basement high areas. So you can see that in the western side, in the same fault alignment, we have one well that is an oil well, the other one is a dry well. In fact, this is not only an oil well. This has become a very good field, and we are producing around 330 cubic meter per day from this particular area. But at the same time, in the eastern side, this is a dry well. So you can see that fault reactivation has something to do it in these areas. You can see that in the dry well, you can see that this is a plan view of the fault. Okay. In the plan view, we can see that both the shallow fault and the deeper fault are joining in the eastern side. But in the western side, in between, in the middle, you can say western middle portion, in the oil well part, these faults are not joining one another. Means the reactivation of the lower fault is not happening, or maybe happening, that is to a very less to the extent that it can breach it. So you can see that the fault juxtaposition also shows in the I did a fault juxtaposition analysis in both the wells, and both the wells should even the eastern side well should also not be a dry well. So this is a study we have done, like this particular fault we are talking about. This particular fault, the blue one and the green one above. So in the area where we call Nadua, these two faults are not joining. We have microscopically, in fact, on a micro level, we have analyzed it and found that this area, the reactivation has not happened, or if it happened, it was to a less extent. But in the eastern side, it has reactivated to a great extent, because of which the well in the eastern side is dry. This is a fault throw diagram, actually vertical throw distribution we have done. So you can see that in the middle, 3 inlines. This is from basically from the seismic inlines. This is basically two-way time versus the fault throw in millisecond. These are all 1, 2, 3, 4, 5, 6, 7. 7 inlines we have analyzed. So out of this, the middle 3, we have seen that the cellular fault is not joining here. Means the reactivation is not happening in this particular. So this fault throw distribution is a very good idea to look at whether even if the play is working, the prospect may not work. So this is another example in Devhal area that we were very confident that this barrel 3 should produce in this particular well. But when we drilled this well, so we got surprised. So in the northern side, even if you see the depth map, in depth you cannot say that this is down. It is only what is happening is the lack of faces. So again, the migration charge risk is there. We have drilled one well in North Kumsai, and just in front of the prolific Kumsai. I don't say it is prolific, the producing Kumsai field, but we could not get any oil or gas in the clays in the Girijan sand lenses that is present in the well. That is why we are postulating. Yes, sir.
Mr. Borgohain,
Yes,
I request you to expedite. We are running out of time, please.
Yeah, I know it, but I'll do it fast. Yes,
Okay.
so you can see that the Girijan in the upthrown side, in the fall block in the upthrown side is getting the oil because of the migration through the fault. However, the in the subthrust area, in the footwall, the well the targeted well could not encounter hydrocarbon. So what is the reason? What are the critical factors for dry wells in Assam Self in last 10 years we have analyzed? So we have seen that this particular thing, that surge failure is one of the important factor. That it is 45% of the total failures in last 10 years wells. Then seal effectiveness is around 25%. Then trap failure is 22%. And reservoir presence 8%. So we have some of the unproven plays, but we think that the North Bank Paleocene Eocene play should work. Maybe we have a Gondwana play in the northern side, or maybe Paleocene Eocene play may have some source rock in the northeastern side at least. Then we have the Songkham Manabum Girijan Namsang Dihing play that I am going to discuss. And we have also some Beryl and Tipam plays maybe present, that is hypothesis only in the grabans also, because some of the grabans we have the Tipams and Girijans and Beryls. So those grabans are not drilled. So we may look at that. Then comes the BCGA. This is the east-west section along Songkham area. Actually, this is the western side is the Manabum anticline, and eastern side is just near the Missimi Massif. You can call Missimi Hills. So from Missimi to Manabum, we have this particular triangle zone, and we are postulating that the Girijan, Tipam, Beryl, those may be lying at a very deeper depth. But the Girijan and Namsang, maybe the Luangs or the Dihings in the Himalayan sequence may also contain some hydrocarbon in this area. So this is a model actually. We are yet to drill these wells, but these wells will be very, very deep. So we have unproven plays called another unproven play we call the BCGA. In many parts of the world, basin-centered gas accumulations is established. Here in just west of Baramura, we have a very good low, and on the southern side also, in the Subhrashis side, we have a low. Maybe these areas could be important for basin-centered gas accumulation. We know even from the Balimara areas, the deeper, even some of the areas, the areas in the deeper side, some of the wells in the deeper side are producing better than the areas that are in the higher side, in the Balimara structure. Then finally, we have come up with some risk matrix, risk reward matrix, and you can see that the highest risk areas are lying towards the northern side of the basin and the eastern side or northeastern side of the basin. So the target play, for target play, suppose one is the target play, one is target play for Lakadong and Langpar, 2 is for Narpu, 3 is for Kopili. These are the target plays for the whole basin. So we are just numbering it in terms of target, and along with that is what is the matrix? What is the risk matrix? Means risk reward matrix. Suppose in the northern side, in the North Bank, the first one, the northern segment is high risk and low reward, high risk and low reward matrix. Then comes the high risk, high reward matrix in the along the Brahmaputra river section. In the central basement high, we know that these are low risk and moderate to high reward areas. So you can read from this particular slide, and you can see that most of the low-hanging fruits have already been drilled. So we have to go for the high risk areas only. So finally, this is almost like a conclusion slide for me. So exploration in unexplored place is the need of the hour. So everybody is telling about this particular objective for our country, because we are setting a target for increasing production from the existing areas and also from the new exploration. So for that, we need to definitely incentivize exploration and moderate to high risk areas. Like if we talk about Kobu Sapori and the Brahmaputra riverbed areas, those are very logistically difficult areas, and the cost of drilling may be very, very high. So I'd like to propose here a national consortium to share the risks for deep drilling. And a national drilling program in line with national seismic program can also be taken up by the country. Okay, finally, thank you for giving me the opportunity to present before this August gathering, this such an important conference, and I hope, like the Rosetta Stone, could enable the historians to know the Egyptian history, because before 18th century, what happened is that the people who wanted to know the Egyptian history, they could not read the hieroglyphic language in the Egyptian scriptures. So what happened is that they found this particular rock where the Greek, Demotic, and hieroglyphs were there, were inscripted in this particular Rosetta Stone, and this paved the way to read the whole of Egyptian history. And likewise, I think the play, if we study plays in Assam or any other place for that matter, it will help us in understanding the prospect, and this will lead to the discovery in future. Thank you very much. But before that, I would like to again reiterate that we need to have a national consortium to share the risks in deep drilling and a national drilling program to go for the high risk areas. Thank you, sir.
Thank you very much, Mr. Borgohain. Thank you very much for your nice presentation.
Yes, thank you, sir.
So now, Mr. Prasanjit, the next event.
So I think the chair is here, so maybe you can invite him.
Okay. So yeah, now I invite Dr. C. Lakshma Reddy to speak out on the presentations and all that. Sum up.